In this video, I will talk about the no cloning theorem. That is a statement that we cannot copy a quantum state. That let's say there's a system, suppose a qubit, and it has a certain state. We know that we cannot copy the state to another qubit or another system while preserving the state in the original qubit. This is called a no cloning theorem, and this was actually realized quite late in the development of quantum mechanics, like in 70s and 80s, and it led to many applications of quantum mechanics, for example in secure communication. But it also posed a challenge in quantum computing, because not copying a state means that we don't have access to the same tools as we do in classical computing. So in this video, I will talk about briefly about the no cloning theorem and show that why quantum state cannot be copied. And then I will introduce a small algorithm with which we can transfer the state from one qubit to another qubit, which of course destroy the state in the original qubit, but we will be able to transfer the state from one qubit to another qubit. So let's uh, dive into it. So the no cloning theorem can be proven in many ways, and I will take the method owing to Scott Aronson and show it using that method. So the setting is like this. Suppose I have two qubits. So this is my qubit Q0, and say there's another qubit Q1, and I assume that initially this qubit is in some state phi, and this qubit is in, let's say, state 0. And suppose we want to see if this state phi can be copied to the other qubit or not, which we can think in this way, that suppose there is some operation, and let me call that operation O, that does this job, and we will see what characteristics this operation O should have and see why this is not allowed in quantum mechanics. So this operation O should transfer, should copy the state in such a way that this qubit retain its original state and the other qubit also gets this state. Now suppose that phi is some arbitrary state, and if it is an arbitrary state, I can write it like alpha 0 plus beta 1, and the copying operation we can, let's say, represent using matrices, because we have learned how to represent multi-qubit states in matrices. So the initial state then is the tensor product of these two qubit states. So on this side, so this is my initial state, and then the final state is the tensor product of these two qubit state, and our operation O has to do this job. So I can write this 0 as, let's say, 1 0, tensor this phi is alpha beta, and this has to go to the tensor product state alpha beta alpha beta. And if I write this using the rules of tensor product, this becomes alpha beta 0 0, and this is going into state alpha 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 square alpha beta and beta square, which means that essentially we want this operation to be performed by this copying operation or copying device, that there is some 4x4 matrix that when applies to alpha beta 0 0 gives us this matrix alpha square beta alpha beta alpha beta beta square. But we see that for this O has to be nonlinear. This operation O has to be nonlinear operation, which means it can never be represented by this matrix so that we get this matrix in the usual matrix product form. So it means since this cannot be a linear operation, because if it is a linear operation, we could only get the combinations of alpha beta and not alpha square. Similarly, we couldn't get product of alpha beta, only get, let's say, 2 alpha plus 3 beta and so on. So since for this operation to happen, for this copying operation to happen, we need a nonlinear operation. So O has to be nonlinear for copying to happen, which cannot happen in quantum mechanics, because in QM we have already seen the postulates which state that only unitary transformations are allowed, which means that since O is not a unitary transformation, this copying operation is not possible in quantum mechanics. So now we see that we cannot copy the state of a qubit to another qubit and keep the previous qubit in the same state. This has led to many applications, and some of them include, for example, secure quantum key distribution and other applications in communication. But our focus here is in quantum computing. So in quantum computing, this no cloning theorem is actually a constraint instead of a resource. So we have to work around this theorem, and let me give you why this presents problem. For example, in a quantum chip, maybe we have a few qubits, but in general we are not able to perform operations between all possible qubits. For example, we might be able to do a control operation between these two qubits, between these qubits, maybe between these qubits and between these qubits and these, but not these. So sometime we have to perform, let's say, a control operation between this and this qubit, but we can't, because there's no link from these two qubits to here, and we can copy the state from here to here by keeping the state here. So we have to come up with ways of transferring this state to some place, let's say nearby, to another qubit which is nearby, and then do any joint operation between them, and maybe transfer the state back to the original qubit that we wanted. So for that, let's discuss a simple algorithm, and let's call it state transfer algorithm. And the problem that we have is this, that suppose I have this qubit q naught, and it has a certain state phi, and then there's another qubit, let me call it some qubit q1, and suppose it is initialized to some state 0, and we want to transfer it, this state, to this qubit. And we don't care what happens to this, because we know that in general we can't preserve this state. So a simple algorithm that can do this job is this. So this is control X operation, and then I'm going to state the algorithm first, and then I'll prove the algorithm. So then you perform a Hadamard on only the first qubit, and then you perform a control Z operation, and then the claim is that we should be able to copy this state from this position to this position. And let's see how we can see if this really works. So the initial joint state at this point, let me call this step 0. So initial state that we have, let's call this state some psi 0. So this psi 0 state, I can write it 0 tensor phi. And I just want to emphasize that there are two conventions of writing the joint state. Some people would write this phi state on left and 0 state on right, but I'm using Kiskett's notation. So I'm putting this 0 on left and this phi on right. And this phi state, by the way, is general alpha 0 beta 1 state. And let me just write it alpha 0 0 plus beta 0 1. So this is our state right at this point. Now the state after the control X operation, let's call it psi 1. I can write it like this. So psi 1 state is obtained after performing control X on psi 0, and this is my psi 0 state. So let's perform control X. So the control qubit is on top, and this is the target qubit. So this is the control qubit, this is the control qubit state, and this is the target qubit state. So since control is 0, nothing happens to target here. So I get alpha 0 0, and this is control is in 1, and so target gets flipped. So I get 1 1. So this is the state that we get after the control X. Now the state after Hadamard on a single qubit, let's call it state psi 2, and so this was a step 1, this is step 2. So state after Hadamard can be written as psi 2. Nothing happens to the second qubit, and the first qubit has Hadamard applied to it. So I can symbolically write it like this. So this is the joint operation Hadamard on the one qubit and identity on the other qubit applied to state psi 1. Now if I look state psi 1 is right here, and I'm only going to apply Hadamard to this qubit on the right. So we know that the Hadamard, when it is applied to state 0, gives us plus state, and when Hadamard is applied to state 1, it gives us minus state, where these plus minus states are defined as 1 over square root 2, 0 plus minus 1. So when it's plus, it is plus here. When it is minus, it is minus here. So when we do this, then we get alpha 0 plus beta 1 minus. So this is the state that we get after Hadamard. Now the final state that is here, let's call it state psi 3. So this state at the output is obtained after this control Z gate. So control Z gate is applies Z gate to the target qubit when control qubit is in one state. And let me just refresh that Z gate when applies to 0 gives us 0, and when Z gate applies to 1 gives us minus sign. So the output state from here is, let's actually go to the next page. So we had, let me just rewrite psi 2. We had obtained psi 2 like 0 plus and beta 1 minus, and we are going to apply control Z gate, and our psi 3 would be control Z applied to psi 2. Now, and before I do that, let me expand this state psi 2, and this becomes alpha 0 1 over square root 2 0 plus 1 plus beta 1 1 over square root 2 0 minus 1. And if we just expand it, so this becomes 1 over square root is common throughout, so alpha 0 0 plus alpha 0 1 plus beta 1 0 minus beta 1. Now this is the state psi 2 that we have, and psi 3 was obtained after applying control Z. Now let me just go back and show that the control Z is like this, where the top qubit is the control qubit, and this is the Z gate is applied to the bottom qubit, and we have written the bottom qubit state on the left side. So control is on the right and target is on the left. So let's go to the next page, and so let's apply this control Z here. So after control Z, just remember this is control, target, control, target, and so on. So when the control is 0, nothing happens to the target, so I get 1 over 2 square root alpha 0 0. Again, no, control is 1, so Z gate gets applied to this 0, but Z gate does nothing to 0 state, so I get this state as it is. And then in the next I have control in 0, which means that nothing happens to 1. Now in the last state, the control is 1, so Z gate applies to 1, but Z gate, when it applies to 1, flips its sign, so this minus becomes plus, so I get beta 1 1. Let's just rearrange everything and see if we can take anything common. So in here I can take alpha 0 common, so we are left with 0 plus 1 here, and in here I can take beta 1 common, and we are left with 0 plus 1 on the right side. So remember there's a tensor here, so left side is common from the left side, and what is left on the right side goes here. All right, so, and again in this and this state we can take 0 plus 1 common on the right side. So this and this are common, so let me put it here, and then this under root 2, let's put it over here. Now this becomes, this is nothing but our phi state that we had initially, and this is nothing but plus state. So it means that the algorithm that I had presented on the last page has transferred the phi state to the left qubit, and the right qubit has gone to the plus state. And let me just show this thing in sort of a summary, that when we started, our left qubit was in 0 state and right qubit was in phi state, and then after our algorithm, the state has gone from right to left, and the right qubit has gone to the plus state. So the state over here is destroyed. This is just some plus state, and the arbitrary state has gone to the left side. So let's just go back to the previous one. So essentially this qubit came to plus, and this qubit became phi, so phi over here went from this side to this side. So it means that this algorithm has transferred the state from one qubit to another qubit. And if you look at this chip on quantum computer, suppose you started somewhere here, so your phi state was here. Now it might have gone to some other state, let's say this qubit. So we have been able to transfer state from one qubit to another qubit. So this state transfer has to be done whenever we want a state present at some other place in our during our computation. So with this, I would like to conclude this small session on no cloning theorem uh, and the use of a very simple algorithm in showing how we can transfer state from one qubit to another qubit using a control X operation, a Hadamard, and a control Z operation.